Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk about one of the gems of elementary number theory, and that is Gauss's quadratic law of reciprocity. In this quadratic law of reciprocity, it's usually stated in terms of something called the Legendre symbol, which I also want to introduce today and is a very important part of number theory. I want to start with a very simple problem to try to introduce and motivate Gauss's quadratic law of reciprocity. Okay, so what's our starting point here? Okay, we're going to fix some prime p, and this prime is going to be an odd prime. And in this particular case, in the simple problem, when the prime is even 2, the answer is very simple, so we can ignore that case quite easily. Okay, and the question is as following. Okay, suppose you have an integer L, and you're just going to look at this L modulo p. When is it a square? That's the question. So I'm going to give you an answer to this question, and it just fits nicely on this slide. So it's fairly simple. Okay, I want to restate it firstly so that you can see the relationship with the problem which motivates Gauss's quadratic law of reciprocity. Okay, so now to be a square just means that you're looking at x squared equals L, this equation, and you want to see when you can solve it. Okay, so for which L does the congruence equation x squared is congruent to L modulo P have a solution? And the answer you can get in various ways, I guess, but it's easiest to approach this by the following simple fact. Okay, suppose you look at the finite field with p elements, okay, and you can look at its multiplicative group of non-zero elements. And the fact is that this group is actually cyclic, so it's generated by a single element. Let's call that u. So we'll use that u later on when we try to understand what's going on. And then what's the order of this group? Of course, is just the number of elements. So since the finite field has p elements and we threw away the 0, it has p minus 1 elements. And since we're assuming that p is odd, note that this is even. So this group has even order p minus 1. Okay, so let's have a look at some facts in this multiplicative group. So you've got this generator u, and what we can do is we can raise it to the power of p minus 1 on 2 here. Okay, and what does that give us? Well, I claim that that gives us minus 1. And why is that true? Because if you have this u to the p minus 1 on 2, okay, so firstly, u is a generator for this cyclic group of order p minus 1. So it's the order of u is p minus 1. So this element here is not equal to 1. But when you square it, you get u to the p minus 1, which is 1. So it has to be a square root of 1, which is not 1. So in fact, it's minus 1. Okay. So now let's have a look at this question of what are the squares modulo p. So essentially you're looking at the squares inside this finite field. Now of course 0 is a square, so we're going to look at the squares of non-zero numbers. Okay, so that's what this is notation means. The squares of non-zero numbers. So you look at the multiplicative group fp cross, and the square here just means that you're looking at the square of all those numbers there. Okay, so let's see what it has. Well, of course, it has just the squares of all the elements. So, of course, you'll have 1, but you'll have u squared, u to the 4th, and we can just list them all this way. Okay, and what you'll notice is that when you get all the way up to u to the p minus 1 on 2 squared, you get back to 1. Okay, so basically, you'll just have u to the even powers like that. Okay, that will list you all the squares. So in fact, if you remove the 0, okay, the squares that you have in this multiplicative group, they form exactly half the elements inside this group, and they're just the even powers of u. All the other ones, so you can look at this as a subgroup of fp cross. So you can look at the other coset of this subgroup, the non-trivial one. Okay, so that equals the set of all odd powers of u. That's u cubed, and so forth. Okay, they're the ones which aren't squares modulo p. Okay, so that's all very well and good. That tells you in the abstract what that is, but how do you get your hands on actually what these are? Okay, so let me show you how you do that. What we're going to do is we're going to apply the following function to these, okay? So we're going to map this over. via the following map, it's just going to send x gets mapped to x to the p minus 1 on 2. Okay, so that's the map inside this multiplicative group here. Now, of course, for all these even powers, okay, when you raise it to the power of p minus 1 on 2, that'll be some power of, that'll be u raised to some multiple of p minus 1, and since u to the p minus 1 is equal to 1, this just gets mapped to 1 here like that. Okay. Okay, so what about all these odd powers? Okay, what happens when you apply this map? Okay, when you apply this map to the odd powers, you can see, well, u of course goes to this minus 1, and then if you multiply it by, if you take any other odd power of u, it also goes to minus 1. Okay, so there are the two cases. Here you get the squares, so other than 0, squares mod p, and here are the non-squares. And the way you detect it is you just raise the number, okay, to the power of p minus 1 on 2. You think of them as inside the finite field fp, okay, and then you raise it to the power of p minus 1 on 2. And if that happens to be 1 inside fp, then it's a square. If it happens to be minus 1, it's a non-square. Okay, so that gives you an answer, and I want to try to write out the full theory of what goes on in this simple explanation here. Okay, so to see how that works, we introduced the Legendre symbol. Okay, so we use this special map. Okay, so the map we're going to look at here goes from FP to FP. We'll call it phi. It goes by various notations, but that's as good as any. And what it does is it's just going to map x to the p minus 1 over 2. Okay. So one of the things to note about this is a multiplicative map. So where does xy get sent to? Xy to the p minus 1 on 2 is just x to the p minus 1 on 2 times y to the p minus 1 on 2. So it's multiplicative in that sense. Okay, so that's the morphism that we were using in the previous slide. And if you want, you can restrict this to just the units inside here. So this restricts to a group homomorphism from FP cross to, well, where does it land? Well, it does land inside the units inside here, but actually you can say more. The image is just inside the subgroup consisting of plus or minus 1. That's a subgroup of FP cross. Okay, that's where it lands. Okay, so I guess the way I wrote the original question, it involves just integers. So what we're going to do is to use this and to express more precisely what happened before, we have the natural quotient map from Z to FP. Okay, so I'll write it that as L goes to L bar. And remember, so why is there a quotient map like that? So remember, one way to think about FP is this FP is just equal to Z mod PZ. Okay, and then this L bar just means the residue class of L modulo P. Okay, so now we can define the Legendre symbol. Okay, so what we're going to do is we're going to consider any integer L. Okay, and the Legendre symbol is usually written like this, L over P, like that. And then what we do is we look at this L bar as an element of FP, and we just apply this phi to it, which is this multiplicative map. Okay, so this is an element of, well, if L happens to be inside, is coprime to P, okay, it will give you a non-zero element. The L bar will be non-zero inside this group of units, so you'll get plus or minus 1. So you can get plus or minus 1. But if it happens to be 0 inside there, then of course this just gives you back 0. And the thing that you want to do is that actually technically you don't want this, okay? You want to more often think of this a Legendre symbol not as 0 plus or minus 1 inside fp, but actually as the integer, either 0 or plus or minus 1. Okay, and there are reasons why that's the case. So it's a little bit subtle, but that's the way you do it. It's the integer 0 or plus or minus 1, which gives you this equality when you look inside fp. Okay, so let's have a look at this. So there's some nice things about this function. So firstly, you can compute it nicely using this formula. Okay, here, using the phi, essentially you've got phi, and this residue class L bar is quite easy to understand. Both phi and this quotient map are multiplicative. Okay, so the composite is also multiplicative in L. Also, since you're taking the definition involves the residue class of L only, it only depends on L mod P. And as we saw on the previous slide, the whole point of the previous slide is that this Legendre symbol, which also gives you another way to define it, is that it detects when something is a square modulo P. Okay, so if L is a multiple of P, of course, then it's going to be 0 mod P, so it's a square. But let's look at the case where L is co-prime to P. Okay, that was the part that we were looking at before, and that's where we look at this homomorphism here. In that case, L is a square mod P is given in terms of the Legendre symbol. We saw that before. That's when the Legendre symbol L over P is equal to 1. Okay, when L over P is equal to minus 1, that's when it's not a square modulo P. Okay, so let's just look at a simple example so you can see what goes on here. Okay, so let's look at maybe the Legendre symbol 2, 5. Okay, so what's that equal to? So I guess what you've got here is that you look at 2 and you raise it to the power of 5 minus 1 divided by 2. So 5 minus 1. So here's the 5 minus 1 divided by 2. That's 4 and 2. That's 2. That's 2 squared equals 4. And that's congruent to minus 1. So it's not a square modulo 5. And you can check this quite easily. If you square 1, of course, you just get 1. If you square 2, you get 4. If you square 3, that's 9, which is 4. And if you square 4, you get 16, which is 1. So you never get 2. So 2 not square modulo 5. Okay, it detects it like that. And that gives you the Legendre symbol. Okay, so that's all very well and good. Let's look at a harder problem, and that motivates the quadratic law of reciprocity. Okay, so now just to remind ourselves, we were looking at this congruence equation essentially. X squared is congruent to L modulo P. And what we did before is we fixed the P, and we asked for which L could you solve this? What are the squares mod P? But now we're going to reverse the roles of things that we're looking at. We're going to fix the L. We're going to fix this equation. So maybe you want to look at x squared minus L more generally equals to 0. And we want to look at this modulo P for all primes. And you want to ask, when can you solve it modulo P? Okay, so this is a general type of question. You're interested in number theory. You want to look at a polynomial equation like x squared minus L, and you want to study it modulo every prime. What's happening modulo every prime? Okay, so of course, the Legendre symbol tells you when you can solve it. Okay, so you want to look at L over P. But the thing now is you fix the L, and you want to say for which P does this equal to 1 as opposed to minus 1. So really, whereas before we were looking at L over P, this Legendre symbol L over P as a function of L where you fix P, and that's quite easy to say what that function is, partly because it's multiplicative in L, and it depends only on the residue class of L. But now what you want to do is, how is this Legendre symbol L over P a function of P? And that's a much more difficult question, okay? So I'm going to give you the answer, which is written in a rather interesting way in Gauss's law of quadratic reciprocity, but was actually conjectured by Euler and others beforehand. And to do that, I want to introduce some notation. If you have an odd number n, I'm going to define this function epsilon n as follows. It's just going to be n minus 1 on 2 So for example, if you want to know what is this Legendre symbol LP, this is just equal to, so I guess what I want to say, if you want to look at -1 P, for example, this Legendre symbol. So remember what you do is you just raise it, this top number here, that's -1, to the power of P minus 1 on 2, which is this epsilon P. Okay, so that's an example of where this occurs. Okay. Okay, so I'll do this in the special case where L and P are odd primes. Okay, a statement of that. And so we're going to look at this Legendre symbol, L over P, but we're going to think of it as a function of P. So Gauss's quadratic law of reciprocity relates this to the Legendre symbol P over L. Okay, so it's not equal to P over L, but it's related in this very simple way. It's that multiplied by epsilon of P times epsilon of L. Okay, so this number on the right here, it's quite easy to calculate, right? Epsilon P is quite easy to calculate. You just subtract 1 from P and L, these odd primes, and divide by 2, and you multiply those two. Okay, so that's going to be plus or minus 1, easy to calculate. And the point is now, whereas this here, if we're thinking of this as fixed L, and you want to think of it as a function of P, you've related it now in terms of this easy quantity here, and this quantity where you've swapped the roles of the P and the L. Okay, so now the L is fixed here, so basically you just need to look at P modulo L. So the answer to this question, interestingly enough, okay, just depends on what P is, the residue class of P modulo L. So it's in this way that the Gauss's law of quadratic reciprocity answers this question, okay? Okay, how is this LP a function of P? Okay, what's a nice way to do it? Well, the point being that it's easy to say how this is a function of L, okay? Because to compute this, to define this term, if you want to think of this as a function of L, you look inside FP, one fixed finite field, and you look modulo P. Okay, and it only depends on L, the residue class of L. So now you've reversed the order here, and so even though now P is changing, that's okay. Okay, so this is an absolutely wonderful theorem which tells you a lot about mathematics, and has driven a lot of number theory. So Hilbert wanted to generalize this in as many ways as possible, and that was one of his problems that he posed in his 1900 address to the International Congress of Mathematicians. What I want to do is just kind of hint to you why it's true. I want to sketch to you the proof. There are lots and lots of proofs of this, and the following one is taken from Serre's A Course in Arithmetic, which is a wonderful book. And I don't want to go through the full proof, but I want to tell you some of the main ideas which are very, very important in it. Okay, so the first thing is something called the Frobenius homomorphism, which is vital to the study of positive characteristics in the commutative case. So you can look at it here, R is any commutative ring. And we're going to assume we're in characteristic P, so we'll assume that P equals 0 in this ring. And in this case here, you have a Frobenius homomorphism. So what is that? So that's a homomorphism F from R to R. And it just sends Y gets mapped to Y to the P. And the point is this is a ring homomorphism. So why is that? So if you have F of YZ, here's YZ to the P. That's Y to the P, Z to the P. So that's actually easy. It's F of Y plus Z. Why is it additive? This is the thing that's rather interesting. And this is where the fact that it's characteristic P is very important. So this is Y plus Z to the power of P. And how do you expand that? Well, firstly, you're in a commutative ring, so you can use the binomial formula. Okay, so in the non-commutative case, something that's really unfortunate is that you don't have this Frobenius homomorphism, okay, because this binomial formula no longer works. But here you do, and so you can start off with the first term as y to the p, and the last term is z to the p. So this is the f of y, and this is f of z, and then there are all these terms which have these binomial coefficients, which are all multiples of p. So there's p times something in there. And of course, this term here goes. So you find that f of y plus z here, this f of y plus z is just f of y plus f of z. Okay, so this is an extremely important tool in the study of finite fields and number theory more generally. Okay, so now I can just sketch to you how the one proof of this Gauss's law of quadratic reciprocity works. Okay, so what we're going to do is the following. Okay, we're going to start with some primitive nth root of unity inside the algebraic closure of this finite field Fp, and we'll call it omega. And this proof and this type of idea occurs very generally in mathematics. It involves something called a Gauss sum. Okay, so it's a sum, so I'll call this Gauss sum just sigma. Okay, and what is it going to be the sum of here? So what I'm going to do is I'm going to look at powers of this omega. So I'm going to write here omega to the x. And since these are nth roots of unity, they only depend on uh, integers modulo L. So you can think of this as just being elements of the finite field with L elements, XFL. And then here, what I want to put here is just X, the Legendre symbol XL. So remember also this Legendre symbol, I mean, it's not written exactly the way I've stated it here. Normally you have an integer up here, but remember this, it only depends on this x up to its residue class modulo L, so you might as well just pick x inside this FL. That's fine. Okay. So similarly, remember you've got an omega to the power of x here. This is not an integer, but since omega to the L is equal to 1, okay, this quantity, to define this, you only need to know what this x is modulo L. So it's okay to do this as x inside L. Okay, so this is the special tool that you're going to use to work out what is to prove the quadratic law of reciprocity. So what we'll need now are two rather interesting computations, and I've written it down in this lemma. So the first one is, what is the square of sigma? The square of sigma gives you more or less L up to this sign, and that sign is minus 1 to the power of epsilon of L. Okay, the other thing that's interesting is that if you want to work out what is uh, sigma to the power of p minus 1, you get the Legendre symbol p over L. Okay, so that's what you've got there. Okay, so let's just digest what's going on a little bit. Okay, so remember this works, you can vary L if you like when you look at this, and if you want to vary L, what this sort of gives you is, what this first part gives you and what this Gauss sum really gives you is, it's a formula for the, by part one, a formula for the square root of L, more or less. It's a formula for the square root of L uh, uh, where you get it by writing it as a linear combination of roots of unity. Okay, so that's rather curious, is that you can actually, inside here, okay, so the first point is, well, do you know what the roots of unity are? Well, let's suppose that we do know what they are, okay, the nth roots of unity inside this FP. So if you're given that, then you can write down all the square root of any odd prime L like that. Okay, so that's the first part. And the second part is what we're going to use to complete the proof. Okay, so let me firstly show you how this gives you the quadratic law of reciprocity. Okay, so we're going to start with this second part, which is the Legendre symbol P over L. Okay, so putting the two lemmas together, both parts of this lemma together, you see the square is this. So if you have P minus 1, on 2. So what does that give you? So what you can do is you can write this out as minus 1 to the epsilon L times L to the power of P minus 1 on 2. Okay, so you're working inside um, uh, FP, if you like, here. Okay. Okay, so now you've got that. Well, what does it mean to raise something to the power of P minus 1 on 2 if you're inside FP? Okay, that's the thing which gives you the Legendre symbol. So this is just the Legendre symbol of P of minus 1 to the epsilon L, L. Okay, and then what do you have here? So remember, the Legendre symbol is multiplicative in the top. So you can rewrite this in terms of the Legendre symbol L over P times the Legendre symbol minus 1 epsilon L over P. And the key point is that this last bit here is just, well, how do you work out what this Legendre symbol is? Well, you just raise it to the power of P minus 1 on 2. So this is just epsilon L times epsilon P. And that gives you the theorem once you know what know these two computations in the lemma. Okay, so I don't want to go through the proof of this lemma, but I want to give you some of the ideas that's involved. Okay, so at the moment, all I've done is given you these two computations. And what I want to do is I want to motivate for you, why is it interesting to look at this Gauss sum? Where does this expression kind of come from? What's going on here? Okay, so the proofs of both of these lemmas use similar techniques. It's fairly elementary, and I want to show you what those techniques are. Um, so that you can see how the definition comes about. Okay, so one is actually harder. So I'm just going to do part 2, which fits on this slide just, but it will illustrate the important points that come out. Okay, so let's have a look at this thing here. So the two facts that you basically use is just the fact that here you've got linear combinations of powers of this fixed omega. Okay, that's the first point. And the second fact that you're going to use is that this Legendre symbol is multiplicative in that top x here. Okay, they're just the two facts we'll use. Okay, so let's see what goes on. So the way I'll do this is actually I'm going to work out what sigma to the p is. So this is equivalent, of course, to sigma to the p is equal to p over L, that Legendre symbol, times sigma. Okay, and once I do that, I'm done. Now the key point about the sigma to the p is here we're working inside this algebraically closed field of characteristic p. So you've got the Frobenius homomorphism. So basically, since this is a ring homomorphism, to take the pth power of this, you just take the pth power of everything. So you have sum over all these x's, and you have the pth power of this Legendre symbol. Okay, the pth power of this Legendre symbol. And then you have this pth power of this omega to the x, which is this lth root of unity. Okay, and note that this is still an lth root of unity. Okay, because you've just taken some power of an lth root of unity. So that suggests that it could be related back to itself. You want to show that it's equal to this expression over here, this Legendre symbol P over L times sigma. Okay. Okay, so let's just see what's going on here. So the first point to notice is that, well, this Legendre symbol is either plus or minus 1. If you raise it to an odd power, it stays plus or minus 1, the exactly same one. So if it's minus 1, you raise it to the odd power, it's still minus 1. If it's 1, you raise it to any power, it's still 1. So it doesn't change. So this x over L to the p is just x over L. Okay. And this sum is over all x inside the field. Okay. Okay, so now what are you going to do? So now you do the following. You do change of variables. Okay, so you're going to have z equals px to make it look more like the original one here. Okay, so when you do z equals px, what you have, so this is just, remember this, you can drop the p here. and then that x is just z p inverse L, and this is omega to the z. And this z runs over what? Well, since P is going to be a unit inside FL, this just runs over all the elements of FL. Okay, so now you've got a linear combination of powers of omega, and you can ask, is it related to the, how is it related to the original linear combination of the powers of omega? Okay, and it's quite easy to see. You just use the multiplicative property here. Okay, so this is equal to, this here is equal to what? Well, you can pull out the P inverse L, and then what you'll have left is this sum Z L omega to the Z. So that's just P inverse L, and this here is just the original linear combination of those roots of unity, which is sigma. And then the only thing that you have to realize is that, of course, P squared is a square modulo L, and that tells you straight away that this Legendre symbol P inverse over L is the same as P over L. And that completes the proof of this second part here. Okay, so just note some of the things which are extremely important here. The fact that you use the multiplicative property of the Legendre symbol. And here we're playing around with powers of this omega. Okay, so that when you raise it to some sort of power, P, okay, it just swaps all these terms around and you can rearrange the sum. Okay, so it's some of the symmetry. So this is basically a symmetry type of result. Okay, that allows you to extract this rather nice fact here. Okay, and to prove this expression here, it's more complicated, but that's the type of thing that you use, and you use a little some more facts about roots of unity here. Okay, so for example, the sum of all the roots of unity is equal to 0. Okay, so that finishes the sketch of the proof of Gauss's quadratic law of reciprocity. And if you want to see where I took this from, you can look at Serre's A Course in Arithmetic, which is a wonderful book as well. I hope you enjoyed this adventure in pure mathematics.